topic for you today. I got to ask Dr. Ball to bring his Geiger counter to see who's hot and who's not. All right. Today's speaker is one of our own. Again, today we're unusual to have so many of our own speakers in science seminar, but today we have another one of our own speakers, John Tixier, who is here with us. He hasn't been with us for very long, just a few years. So it's kind of nice to see what he's done before he came to Letourneau. John has his bachelor's in mechanical engineering from the University of Wisconsin. Okay, so he's a Yankee. Good. Fellow Yankee from Iowa.
Cheesehead. Cheesehead.
And he has his master's in mechanical engineering, I think it is, from the University of California, Berkeley. Okay. And before John came here, he had another life. He worked at the Pacific Northwest National Laboratory, which as a chemist, I know it's a place where NW Chem, chemistry program, was birthed out of there. And so it's a good place to be from, NL, as we call it. And he's done a lot of work here with waste management. Not just ordinary waste management, but nuclear waste management. Okay? And he can tell you a little bit about that today. All right, so let's give John a warm
Thank you, Dr. DeBoer. It's an honor and a privilege to be here to share with you guys some of the things that I've learned in the past and some of my work experiences as well, and hopefully it pertains to science and pertinent to a science seminar. So as Dr. DeBoer said, I'm John Tixier, assistant professor here. I want to give you a little bit of introduction. I want to thank Dr. Lichtenberg for leading us off last week. It was a very interesting discussion, and there will be some things that sort of relate. First, though, I wanted to say that I'm actually a little bit concerned about, just from a biblical standpoint, about space exploration and even commercial flying. I mean, here I have over 1 million miles of commercial flying, and I'm concerned because Jesus said in the Great Commission, he said, "Lo, I am with you always, even to the ends of the world." He didn't say 30,000 feet. He didn't say 470 kilometers above the earth, right? Lo, I am with you always. So just a little bit of hesitation on that. All right. So I'll go through, introduce a little bit about myself and my background. We'll get into a Radiation 101 explanation. I don't know how much exposure you've had to radiation, and no pun intended, in your studies, but we'll talk some about that to get you up to speed on radioactivity and how it relates to chemistry and physics. Then we'll talk about some engineering applications that I've been involved with. And finally, hopefully we can have some questions and answers, and I've got some demos, some demonstrations for you. So try to fit it all in here in the next 45 minutes. Just by way of introduction here, as Dr. DeBoer said, I spent the last 26 years of my career before I came here last year at the Pacific Northwest National Laboratory in Richland, Washington. This is a view from the mountainside up outside of Richland, Washington. So we have a few mountains. We're a little bit east of the Cascade Range. We have no trees there unless we plant them. Okay, we don't get much rain there. 7 to 10 inches of rain a year. But if we water the grass, it grows. If we plant trees, they grow. Legacy of the Manhattan Project. I'll talk a little bit more about this in a minute, but that's a bomber from World War II, and it was intimately connected to the work that went on at the Hanford site. So you can see the Pacific Northwest and eastern Washington, part of the Tri-Cities, Kennewick, Pasco, and Richland, Washington. So when people think of Washington, they usually think of rainy. In fact, I had people, when I moved here, think that I wasn't used to the heat or how dry it was. I said, no, I'm from eastern Washington. I'm used to heat and dry. I'm not used to the humidity. Still getting used to the humidity. All right. Here's my family. My children, many of you know some of my children because they're students here. This is a picture at Mount St. Helens in the Pacific Northwest that we got to go a few years ago to on a camping trip. So my oldest son, second from the right, is Daniel, and he graduated from Laterno in 2013. He's now an air traffic controller in Kansas City. So he was able to take his air traffic management degree and actually start a career in that field. The one in the middle, David, many of you know, he's a student here, sophomore this year. And on the left of David is Stephanie. She's also a student here. And so it's a joy to have a couple of our children here at school with us. The two on the ends are Biola related. The one on the right, my oldest daughter, graduated from Biola in 2015, and she's now studying physiology. She graduated with a degree in human biology, and she decided to go to grad school after she was finally able to quit her job at Starbucks, because there's not a lot of jobs for human biology majors as there are for nurses. But she liked the science better than the nursing part, than the patient care. And so, but she's decided to take that on and go to grad school. She's at the University of Arizona studying physiology. And the oddball on the left, the one who's not into science-y kind of things, is Lisa. She's at Biola. She's a senior there. She's majoring in art and design. So we're fun. It's fun to have our kids here for the summer. Everybody's here this summer. And my wife is here with me today, sitting in the front row. This is a picture from over 30 years ago when I was in grad school. So I didn't need to show a modern picture. She's here. Suzanne, in the front row, thank you for coming. So that's a little bit about my family. Let's talk about radiation. So here's a picture from the Hanford site back in the 40s when they built the place up in order to produce nuclear materials, which contributed to our winning the war, World War II. So it's a very pro-nuclear area. Nuclear power, nuclear energy, all things nuclear are viewed favorably there. We have a power plant, nuclear power plant here on the left. That's a view that's a little bit over the hill, almost a view from my backyard, but from where we used to live, but a little bit over the hill from that. But this is not a mushroom cloud. This is a steam plume coming out of the power plant. So we have a nuclear power plant nearby. It's on the Hanford Reservation. It's not part of the Department of Energy complex there, but they produce nuclear energy for the Pacific Northwest, part of that Northwest Energy complex, including hydroelectric there. We're so pro-nuclear in our area that the local high school is the Bombers. And their symbol is a mushroom cloud. Okay? So they've been accused of not being politically correct in the past, but the actual source of that, from this picture, the day's pay, the Hanford workers, back during World War II, the 50,000 men and women that were there working on projects to produce nuclear materials, they all donated a day's pay to buy a bomber for the war effort. So that's the legacy of Richland High and their bomber symbol. So when the Japanese delegation came over some time back in somewhat of a protest of saying, hey, you know, that's not something that we appreciate, the response from the school district was, we didn't start the war. So that's, and so it still remains. They still are the bombers, right? I'm just reporting the facts, okay? It's just the facts. It's just what happened. Right? But in some areas, they are what we call anti-nuclear. They are against nuclear things. And so at the University of California, Berkeley, they're very anti-nuclear. They didn't know there was a nuclear power plant in the engineering department when they declared themselves a nuclear-free zone. The high school, even the local high school in Berkeley, to contrast, voted themselves a nuclear-free zone, including the airspace above themselves. They wanted to make sure they covered everything. To be nuclear-free. We'll see, hopefully in the presentation you'll realize how sort of ridiculous that is, the concept of being anti-nuke or nuclear-free zone. Okay, so nuclear physics is pretty complicated subjects, and I'm not, as contrary to what was mentioned, I'm not an expert in it, but I've had some experience with it, and so I'm going to share some of that with you today. So let's talk about the science of radioactivity. Right? Hopefully everybody knows what an atom is and what an atom is made up of. If not, why, I think both Dr. DeBoer and Dr. Ball are going to be upset if everybody in here doesn't know the composition of an atom. All right? So you've got protons and neutrons in the middle. You've got electrons swirling around the outside. Of course, in the middle is a nucleus, right? So that gets us all up to speed on that. Maybe I'm a slide behind. So we relate all those into the periodic chart, right? Somebody figured out some symmetry and some things that go together and put it all in the periodic chart. So hopefully most of you are familiar with the periodic chart. And from the periodic chart, we can get a lot of information about each atom, about each element, not each atom, each element that's involved in our, that we're studying. So we have, I wanted to use the screen here. I wonder why that went away. Let's see if I can do this. Display control. It's not going to be a disaster if it doesn't work, but I was hoping that it would work. Let's see if those come on. Okay, so here's that. Let's put this a little bit to the right so I can use the pad of paper. Okay, so if I write on here, you guys can see that, right? Okay. All right, so let's pick out an element here, lithium. Anybody ever work with lithium? What's the atomic number of lithium? 3. And what does that mean?
It means it has 3 protons, and if it's a neutral atom, it also has 3 electrons.
I have a prize for people. I'll tell you more about that in a little bit. Okay, 3 protons, and then what's the atomic mass? What does the atomic mass mean? I don't know. Don't say that out loud. The atomic mass. Okay, so the atomic mass is the sum total of the mass of the protons and the mass of the neutrons in the element, right? And so when you look closely at the the periodic table, those are not whole numbers. The atomic mass is not a whole number. The atomic number is, but the atomic mass isn't. Why is that?
Isotopes.
Because there are isotopes, right? And so for lithium, element lithium has atomic number of 6 for atomic mass of 6 for 7.59% of the lithium has an atomic mass of 6, and atomic mass of 7 is 92.41%. So we take the weighted average of that, right? 6 times 0.0759 plus 7 times, I wrote that wrong, right? 92, that's a 92.41, times 0.9241, and we end up with the atomic mass that is displayed on the chart of 6.94, right? So atomic mass is a weighted average of the isotopes. Okay, does that make sense? So that's the atom and how it shows up on the periodic chart. Energy levels. Radiation characteristics start with energy levels. We're talking about decay and half-life because those are characteristics of radiation. So let's look at the energy levels. There's 2 types of radiation. Ionizing radiation is what does damage to your body. That's what people are concerned about. Okay? And there's non-ionizing radiation. Okay? So the ionizing radiation, that's what you think of as nuclear things. Non-ionizing, what are some characteristics of non-ionizing radiation? Microwaves. Who said that? Who has a microwave? When you microwave your food, you might call it nuking it. I nuked my food. You're not going to go nuke my dinner. You're not nuking it. You're not using nuclear energy, okay? Nobody needs to be afraid of getting nuclear exposure, radiation exposure from your microwave, okay? It's just radio waves that are heating up your food. They make the molecules jiggle faster, so it heats up the food. So when you put your goldfish or your hamster in the microwave, anybody? Okay, you're cruel if you do that, okay? Because you cook them. You're not nucleing, you're cooking them. You wouldn't want that done to you, so don't do that, okay? Don't put live animals in the microwave, all right? Okay, and so, yeah, your cell phone is electromagnetic radiation, but it's not ionizing. Cell phones don't cause any damage, right? Okay. Who knows? Maybe they do, but it's not from nuclear energy, okay? So nuclear or radiation is also characterized by decay, right? These isotopes are unstable. Radioactive isotopes are unstable in the nucleus of the atom, and they eventually give off a piece of it and send it out, okay? And they change state, and so they decay. And so eventually, potassium, for example, as an element, potassium has several naturally occurring isotopes. So it has an atomic mass of 39, 40, 41. Okay, those different, and so that gives it its atomic mass, right? Atomic weight. Potassium 40 is radioactive. Potassium 39, potassium 41 are stable. Potassium 40 is radioactive. So there's a little bit of potassium 40 in all the potassium. So what do you find potassium in? Bananas, yeah. Milk has potassium in it. Lots of things that we eat have potassium. So we're ingesting radioactive materials when we eat a banana, okay? You are exposed to radioactive materials in the environment, okay? So when it decays, when it changes its state. It gives off a particle, and eventually it becomes argon. Okay, so that piece of potassium, that little potassium atom, gives up a part of it, and it changes into argon, okay? So that's how decay works. It gives off a piece of it, it changes into another type of atom. Concept of half-life. All of this can be statistically evaluated, okay? So there's, as far as the amount of stuff in there, if it's radioactive, if it's decaying, half of it will decay over a certain known period of time. So if you have a certain amount of it, half of that will decay it according to its half-life. So if its half-life is, say, 20 years, then after 20 years, you will only have half of that left. This half will be converted into something else. 20 more years, you have half left of what was left over. 20 more years, half is left. 20 more years, and it keeps going and going and going like that. Okay, so that's the half-life. In that amount of time, you have half of it left. Okay? It's a statistical average. You don't know which atom is going to decay next, okay? But just of the bulk of it, then at least half of what's in there, some half of it is going to decay, all right? We don't know which one. It's a statistical average. All right, so that's some radiation characteristics. Now let's look at types of radiation. There's 4 or 5 types of radiation, okay? I'm going to characterize each of these for you. They're all assigned a Greek letter. Most of them are assigned. There's some other terms that we're using. But they're assigned a Greek letter. I used to think, as an engineer, you learn a lot of Greek letters, right? And all your equations and symbols and formulas, you learn all about the Greek alphabet. So I thought, you know, when you take Greek, if anybody's going to take Greek, you got a heads up. You got a head start on taking Greek because you know the alphabet already. until I took Greek. I realized that lasts about a day. Okay, then it's all Greek after that. So it's a bit challenging as you learn vocabulary and grammar, but at least you got a head start on the alphabet. All right, so the first 3 letters of the Greek alphabet are used to distinguish different types of radiation, and they're listed in terms of increasing, I would say, maybe say hazard, energy level is maybe more accurate, but let's take a look at these different types of radiation. An alpha particle doesn't travel very far. An alpha particle is essentially a helium nucleus, right? 2 protons, 2 neutrons. That's an alpha particle. Doesn't travel very far, and it's stopped pretty readily. It doesn't have a lot of penetrating power. So it's stopped actually by the dead layers of skin that cover your body. So if you touch something with alpha contamination on it, like plutonium, it's an alpha emitter, if you get it on you, it's not really very hazardous. What's hazardous is if you get it inside you. If you breathe it in or ingest it, you've got no dead layers of skin to protect you. And so it does a lot of damage to the internals of your body. That's why people who are handling plutonium have to be protected. The airspace has to be protected. Sort of like asbestos, only a lot worse. Okay. So you want to be protected from alpha mainly through ingestion. Beta particles. Beta is an electron. So an electron gets ejected out of that atom as it decays. So it has a different charge. It gives off some energy. Beta can travel about 10 to 12 feet in the air. And it can be stopped by a thin sheet of aluminum. So you don't need lead shielding to protect you from beta contamination. And every radioactive element has a different characteristic of what it gives, or a unique characteristic to itself. It doesn't change certain elements. If it's an alpha emitter, it's always an alpha emitter. If it's a beta emitter, it's always a beta emitter. So you can take care of that depending on the materials that you have. All right, so beta can be stopped by a thin sheet of aluminum. So that's what you can use for shielding. We'll talk about shielding in a minute. Gamma particle is actually a photon. It's not a component of the atom. It's a photon. What's a photon? A ray, yeah. Sort of like light energy, electromagnetic energy. It's at the high end of the spectrum, okay? But it's ionizing. It does damage to your body if you're exposed to gamma radiation. And at that point, or the gammas can be stopped by, you need some heavy steel or lead for shielding, okay? You need some heavy materials. Concrete itself, or even uranium can be used it makes good shielding for heavy gammas. Okay, and then X-rays are part of that. They're in the electromagnetic spectrum. They're not as high in energy or wavelength as gamma is. They are higher than the ultraviolet. And so they're also use lead shielding. So when you go to the dentist and you get an X-ray, they put a lead sheet on you, and then they run, okay, to get out of the way. So they don't want to be exposed to that. And then there's neutron radiation. That's not a Greek letter. I don't know why, but the neutron is a neutron, right? So maybe they decided they didn't need to give it another name because it's the internal part of an atom. So it gives off a neutron comes out of that, and it's pretty dangerous too. But it needs hydrogen materials to stop it to provide for shielding. So lead doesn't work nearly as well as water or plastic for shielding, and even concrete because it's got so much hydrology in it for shielding if you've got neutrons. Okay, so those are different types of radiation that you've heard about, and a little bit of information on those. Let's talk about where radiation comes from. Where are we going to find it? How do we look for that? Well, there's several different locations or places that we can experience radiation sources. So we'll look at each of those, and we'll look at it in terms of the periodic chart. So naturally occurring radiation, as I mentioned, we've got potassium. Potassium found in nature, right, as we mentioned, in bananas, in the soil. It's a critical element of fertilizer to make plants grow. You've got radon. Radon is a gas. It's a noble gas. Radon is a byproduct of uranium. And so it's a daughter product of uranium. So as uranium decays, eventually it hits radon somewhere before it becomes lead. So there's a big, long list of things that uranium decays to, and radon's one of them. And it's a gas, it's not a solid. And so there's places in the country where there's lots of radon, and it can build up in your home. Generally, it's not, if you've got good ventilation, it's not a problem. But radon, you don't want to be breathing that in. And so people have to put on, like in Spokane, Washington, there are places where there's pretty high levels of radon gas. And so people have to get their houses tested and put extra filtration and ventilation in their houses to keep from being exposed to too much radon. Other naturally occurring, uranium is naturally occurring. You can mine that and make things out of it, make energy out of it. Thorium, naturally occurring, radium, naturally occurring, and carbon, even carbon. Naturally occurring carbon has a radioactive element, isotope in it, right? You've heard of that. It's carbon dating because we use that way. Okay, medical sources, medicine, nuclear medicine is a field in and of itself. You find radioactive components in medicine, and so some of the things that are common are iodine, the radioactive component of iodine. People get injected with that to use as a tracer in your body, so you are radioactive when you get that. You actually, if you put up a Geiger counter to you, you would be clicking pretty fast, okay, if you have a nuclear medicine treatment. Gallium, indium, thallium, all used in nuclear medicine. Technetium, there's a number of different isotopes. Some are just generally hazardous, but others are able to be used for nuclear medicine. Yttrium is a byproduct of strontium, which is a waste material in the nuclear waste processing, and I'll talk about that a little bit. But yttrium is a byproduct of that. It doesn't have a very long half-life, but people are using that. Some folks at PNNL, where I used to work, and they developed a technique to turn that into little BBs or seeds and inject that into people so that you can get a local treatment of cancer. Doesn't last very long. It's very intense in the spot. So prostate cancer is being treated that way, so that people get injected with a yttrium seed, and so they're radioactive. So you don't have to go to radiation treatment where it sort of zaps your whole body and you're trying to focus it on a certain part of your body, but you get all exposed. They can inject a little tiny bit of yttrium into your body right next to where the cancer is and zap it right there and not have nearly the effects on your body. You're still radioactive. Geiger counter on you, you're clicking away, okay? All right, so there's some medical uses of radiation. Industrial uses. In industry we use radiation. Obviously uranium, industrial use of uranium, right, in nuclear power plants. Americium is used in smoke detectors. So your smoke detector may be radioactive. Thorium, so I'll do a little demonstration with that in a little bit. Cobalt, iridium, barium, cesium, all used in industry one way or another, okay? So all of those things are generally friendly, right? Naturally occurring, medical isotopes, industrial isotope uses. It's friendly, it's useful. In fact, somebody said one time that if the first use of electricity had been to electrocute someone in an execution, we might not have electric lights today, right? Because people would be against it, against the use of electricity, because it's bad. The use of it was bad to begin with. So nuclear energy, the first major use of something nuclear was to blow up and kill a bunch of people, win the war, but generally perceived as bad. Nuclear is perceived as bad, even though it has all these beneficial uses, okay? So let's look at what we really mean when we talk about nuclear, because you don't think about those other things necessarily. You think about these things. These things that are above uranium. Everything here is above uranium. Up to there's lawrencium at 103, and then we pick up at 104. These are all transuranics, okay? They're above uranium in the periodic table. Transuranic elements. Every one of them is man-made. After uranium, that's the last naturally occurring radioactive or a naturally occurring element. Everything else, we got to make it. Make it by changing, typically by changing uranium. By working with uranium, and we produce all these other things. And as I said, some of them are useful, particularly americium and plutonium. Plutonium originally as a nuclear bomb, but now we're using plutonium as a fuel source in space exploration. But we don't want certain bad elements around the world to be getting their hands on too much of these things because they can use them in a bad way, right? So that's what the fear is. Up here at the end, you've got some 3-letter elements up here. UUT, UUP, UUS, UUO. You know what those are? Anybody?
They're unnamed elements up to this point.
You already had a marble, but I'll give you another one. They're unnamed elements, right?
Is this the most updated periodic table?
It may not be.
Because the LV and FL, I don't recognize those.
I don't remember where I pulled it. It says 2015, so a couple years old. UUT is untrium. It's a Latin word for 113. Okay, that's the atomic mass of that element. It's never been made. I said all these are man-made. It's never been made before, but they know it's there somewhere. They know it's capable. It has a place in the periodic chart. And so they've never been able to make it or measure it. A lot of these things, when they make them, they only last for a few seconds. They're very difficult to detect. But somebody claims to have done that. And so they gave it a name after something having to do with the people who were involved in it. So when you look at the periodic chart, they all have some sort of attachment to the people that were involved. And I'm not going to read them all. But I would, of some of these lower ones, I will call out berkelium. The University of California, Berkeley was instrumental in coming up with some of this nuclear research. Californium also was part of the Berkeley research. So it's really sad, if not idiotic, that they want to be anti-nuclear because they're named in the periodic chart for radioactive substances, all right? So pretty weird. That's people don't think through what they're dealing with, it seems like sometimes. All right. So those are the sources of radiation. Effects of radiation. How does it affect you? What happens in radiation effects? All right, so you've got natural exposure. So just because we're exposed to all these things in the environment, we get exposed to radiation. And so some of this comes from all kinds of places. Medical, your x-rays, radon, if you've got radon in the environment, comes from space. There's the food you eat. You're radioactive on the inside, right, because of the food you eat. It's the ground you stand on is radioactive, and some other things. So you are exposed to a certain amount of radiation every year, okay? About 1 millirem or microrem, 1 millirem per day, okay? So that's your exposure. Microrem per hour, 5 microrem per hour is probably the average, somewhere in that range for what we're being exposed to now. And I need to scoot through this so I can give you some examples of what I've done with this before. So we've got different exposures. There's chronic exposure, which means what? Long period of time, right? Take over a little bit over a long period of time. Chronic exposure. Some examples of that are radon exposure, right? If you live in a house with radon, you're being exposed to a little bit over a long period of time, and it can be bad for you. There was an example, too, of back when people were using radium as a glow-in-the-dark substance and putting it on a watch dial or a compass thing so that people could see them in the dark. The ladies that were doing those, the workers that were hand-painting those, would lick their paintbrush to give it a sharp tip. Yeah, it didn't work out well for them in the end. So we learned some things along the way, that some of this is difficult. Didn't happen right away. You're not exposed right away and die. It's a little bit over a long period of time. But there is acute exposure, which is just the opposite. Big dose, short period of time. Okay? Couple of, well, here's some effects. I'm going to go through that. The 300 to 500 rem, that's a pretty big amount. Lethal dose, 50% of the population will die within 30 days if you don't get treatment. Okay, if you're exposed to that heavy of a dose of radiation. LD50. Within 1 month, you'll die. But you can get medical treatment for it at that level. There are levels for which you can't get any medical treatment. The Department of Energy controls the amount of exposure that people get. So they don't want you being exposed to too much. So if you are a radiation worker, you are highly monitored for your exposure. You have to wear a dosimeter. You have to keep track of how much you get. That goes in annually. You get a report. So they keep track. They don't want you being overexposed for that. A couple of movies that I would recommend to you. Fat Man and Little Boy is a movie about the making of the atomic bomb. And those are the names of the 2 bombs that were dropped on Japan. Fat Man and Little Boy. And the plutonium for the Fat Man bomb was made at the Little Boy. Now I get them mixed up. Made at Hanford. Plutonium bomb was at Hanford. The uranium for the other bomb was made in Oak Ridge. So those are partner sites as part of the Manhattan Project. That I don't even have time to go through, but I have the sheet here if anybody wants to look at that for different dose levels and their effects on you and how DOE, Department of Energy, administrates that. So how do you keep yourself safe? You use ALARA. You want to keep your exposure as low as reasonably achievable. You can't prevent everything, but you use time, distance, and shielding as your friends. Okay? A low amount of time exposed, a far distance, and shielding if you need it. Those are administrative controls. That is, somebody makes a decision as to how long you can spend in a certain area. Or they are engineering controls, like putting up barriers and shielding. And so distance can be either one. Distance can be the amount of time, the distance that you have to keep away from it, but if you can't do your work, you might need some robot or something, so that would be an engineering device in there. Contamination versus exposure. What's the difference between contamination and radiation exposure? These guys are working in a contaminated area. They are suited up. So they don't want to get any on them. Okay? If you're contaminated, you've got radioactive materials where you don't want it. You can contaminate your fridge by spilling something in it, and it gets all sticky, right? I'm not talking about radioactive contamination. I'm just talking about something where you don't want it. It's contaminated. You got to clean it up. So that's what we're doing at Hanford, is cleaning up a lot of stuff. So these guys are not, there's not a lot of exposure as in radioactive dose, even though they're keeping track of it. In this is a hot cell. This is where the stuff that's inside of this is highly radioactive. So there's lots of shielding. The window there is discolored because it's lead glass to keep the radioactivity from coming through. And the guy on the outside has to work with a manipulator. He has to use this device here in his hands to make the end effector in the room do something useful. Okay? So these guys get very skilled at doing that. It's very hard. All right, so let's look at some radioactive waste remediation and radiation detection that I've been involved with. So first, they made those nuclear bombs, and then they made more of them, and more of them, and more of them. And obviously we don't have time to go into how to make a nuclear bomb, and I couldn't tell you anyway. I'd have to kill you after that. So it works out good for both of us. We're not going to take too much time to do that. But splitting the atom, making uranium into something useful so that you can make it into a bomb or make it into fuel, actually, produces a lot of waste products, fission products. Strontium and cesium are some of the primary fission products, but a lot of radioactive waste comes out of that. Incredible amount of radioactive waste. This is the Hanford site. 560 square miles of land that was commandeered in World War II to build the B reactor that produced the plutonium to build the bomb that dropped on Nagasaki. Now, a lot of it has been cleaned up, but there's two main areas where we've got some processing. I won't go into all that. This is the modern area where they're building a system to treat all the waste that's left over from this site. The waste is stored in these huge tanks. These are 75-foot diameter, 50-foot deep, million gallons. They hold 1 million gallons each of radioactive waste. There's 150 of them that they pumped different waste into it and reprocessed over the years. It's a chemical nightmare. The best way to dispose of that, to treat it, is by vitrification. Who knows what vitrification means? Yes, who said that? Yes. You make it into glass. And what better way to dispose of it than to turn it into little black marbles and hand it out at presentations? Okay? these are just little black barbels. Okay, they're not radioactive. All right, vitrification, making glass, vitro, in glass. Okay, so this is a picture of a melter right here. This is a melter. You've got electric electrodes taking some waste, some glass, there's more glass ingredients to make it into a glass that can go into a canister and be disposed of. This is a sample of something that's heated up in an oven of those glass formulations to put into just as a sample in an oven. So because we want to study the glass formulation to realize what can do the best for us in containing the radioactive waste. All right, so this is that big plant that they're building, the waste treatment plant. So some of you guys are familiar with waste treatment plants as a wastewater treatment plant. This is the biggest waste treatment plant in the world that's being built to dispose of the radioactive waste at Hanford. But we've also figured out how to do in situ vitrification, how to vitrify stuff in place, right in the ground, right where the waste exists, by turning it into glass right there, by making our own little lava pool, by heating it up and turning it into a big rock. And that's what I was involved with some. Here's a picture of that set up at one of the reactor plants where they had a disposal pit where they seeped some of that radioactive liquid waste into the ground, and now it's left as a problem after they realized 30 years later that that wasn't such a good idea. But it was a good idea at the time, okay? Here's sort of what it looks like at another site. So this is halfway excavated, so that's a big solidified glass rock that was made, man-made, by just heating up the soil, the natural soil there, and melting it into a big rock. This is what it looks like on the inside. It looks like a pool of lava. It looks like a little volcano going there, a little bubbling pool of hot lava. I'm going to skip that. This is what it looks like on the outside. This is a pilot scale demonstration. In fact, from that other site here, this rock up here that's been pulled out of the ground, that's the one we're looking at here with the former division director standing there. If you're, just an aside, if you're a professional photographer or if you're taking pictures of people, try to line up your shot and see what's in the background. And try not to have the equipment that's sticking in the back make it look like a pipe is coming out of the guy's rear end. For all time now, it looks like that. Yes?
So when nuclear waste is vitrified, either like this or like that, is it no longer hazardous?
It's still radioactive. It's just safe. And so I'll show you this here. This is a chart of a leach test of how durable is this glass. We can perform, the government has leach tests to see how fast is this stuff going to decay. And so there's certain tests. The units aren't necessarily important, but the comparison is, so bottle glass will decay after, and by decay I don't mean radioactive decay, I just mean, wearing away in the environment. Marble, granite, the vitrified soil that we've done is on the order of Pyrex glass, which is extremely well made, right? You got to take good care to make that, as opposed to bottle glass, which isn't necessarily as well made. But it's the point is it's extremely durable in the environment. It lasts for geologic time frames as long as the stuff is bound up. That's what you want to keep it from being mobile in the environment. Right now it's in these tanks. The tanks are leaking. The radioactive waste is getting into the environment, and so we need to stop that. So they're building that big plant to take all that waste and feed it into a system that melts it and puts it in canisters. And then those canisters are going to go to some waste repository somewhere, which hasn't been decided yet. Or it was decided, and now it's not being decided.
Is it true that salt water actually dissipates the energy of radioactive materials?
I'm not sure. I can't. I can neither confirm nor deny that. Sorry. There's a lot more chemistry that I don't have time to get into, but I'm sorry that I didn't have time to tell you about some of the chemistry and research that we did on the properties of these things, because I want to show you a demonstration. So Dr. DeBoer said that he was hoping that Dr. Ball might have a Geiger counter. I have one. I have a Geiger counter. So in fact, I have two of them. And if anybody is interested in turning their phone into a Geiger counter, I need a volunteer. Does anybody want to turn their phone into a Geiger counter? Hoping that this will work here. Poor man's Zoom. Okay. So that's a Geiger counter. I should try to turn on the speaker on. Okay. Okay, now it's clicking away. Okay, so there's our background, 0.08 microsieverts. So I said earlier that the background was around 5 microrem per hour. So this microrems are about 100 times bigger than a microsievert. So we're around 10 microsieverts, 5 to 10. Questions? Oh, you want to be the phone guy? Yeah, come on up here. Turn your phone into a. All right. So you need to. I'm going to skip through. I don't even have time to tell you guys this stuff here. All right. You need to download. Go to Google Play or the App Store and download FT Lab or Smart Checker. Okay, FT Lab or Smart Checker. Anybody can do this if they want to play with this later. It doesn't make your phone radioactive. Okay, so I went to the store to see what sort of things I could find. So here's some grinding discs that were, you can see what the background is here, showing now my counts are around 18. So I went there and I looked at this grinding disc. It was getting 12, so the same order of magnitude. One grinding disc wasn't doing anything, but I put it on the stack of grinding discs, and I got 35. So about double of what the background is. So when the other thing that I was involved with was detection of radioactivity at the borders for national security, because now that the Cold War is won, there's bad guys that can get their hands on radioactivity, and they may want to do bad things to us. So Customs, U.S. Customs, is trying to prevent the illicit import of radioactive materials. And so I've been involved in that and putting out detectors at the borders for that. And so when they get a shipment of grinding discs, because it's just a big Geiger counter telling you if there's radioactivity there, of elevated levels of radioactivity, they get an alarm. So you got to sort through that and figure out, well, what is it? Is it good or bad? Is it safe or not safe? You got it?
Yes, sir.
Stick that in your probe. Okay, another thing that I found, clay tile or ceramic tile in the store was on the same order of magnitude, right? 36, so about double natural background. So you get a big truckload of that, and it's radioactive. So the tile that you're walking on, any earthen materials, they contain some potassium, some thorium, maybe some uranium, I don't know, in your household. So that's where you're getting exposed to this stuff.
So what's the danger level on the Geiger counter? Like,
The danger level is going to be 1,000 times this or more. There's no danger to what we're being exposed to here. Kitty litter, same thing. All right, I've got something for you to do in a minute. All right, so this kitty litter, earthen materials, concentrated. All right, I have some uranium. If you could, it's clicking pretty fast, and it's going up pretty steadily. Why don't you put your, let's see if that can pick it up here. It's not nearly as sensitive, the little thing. Can you see what's going on there? Can you read the counts there or not? Is that there? I mean, 217. Does that work? Does that wash it out? Okay, 250. You know what else is radioactive besides uranium? Camping equipment. Coleman lantern mantle. That's more radioactive than uranium. You see what's in here? It gives me the properties. Oh yeah, this doesn't show up. You can't really read it. It's thorium. Thorium is part of old Coleman lantern mantles. I found one of these in my parents' house, but they hadn't used their camping equipment for a long time. Modern Coleman lantern mantles are not radioactive anymore because they got rid of the thorium, so they don't work very well either. They don't last very long. But the old-fashioned ones with the thorium in there, they maintain their status pretty well. My app on your phone is not working very well. I didn't, that's basically it. I skipped over a lot of the radioactive detection at the borders, but I'm here for questions. It looks like people are needing to leave. Sorry about that. Happy to answer any questions. Conrad? Oh, we had a lot better Geiger counters than this one, so he was on the job.
I want to remind you, next week, we'll have a special science seminar on the solar eclipse. So you want to come out and come.
So, I don't know why. Oh, yes, thanks for your input. So there it's going. We didn't push on it.
Oh, okay.
Okay, so now it's going. So the app is working. It's getting some reading. Yeah, thank you. Yeah. It should be the same. It may not. This is not nearly as good as.
What is that, a lantern mantle?
Yeah, Coleman lantern mantle.
Oh my word, I don't know how many of those we used camping years ago.
Yeah, if you still have a pile of them somewhere, the old-fashioned ones.
Yeah, no.
They're pretty highly radioactive.
Very interesting.
Yeah, good.
Oh
Thanks.
man.
Yeah, so
But
you're
they
getting.
sure put out
It's
the
getting
light.
close. I'm at 7. Yours is at 5.5.
Yeah. They sure